Let us calculate the relaxation time scale for dynamical friction. Let's consider the geometry below. You have an object, a mass m, that is traveling with relative velocity v. In a time interval dt, it crosses this distance here, v dt. The object is encountering stars at an impact parameter b. We want to integrate over all of the impact parameters to know how much energy is being transferred to this object. We also need to know how many stars, the number of stars that are colliding. Now, because this is continuous, there are too many stars, we need to consider distribution. So we are going to consider f to be the distribution of stars. This quantity f dv is the number of stars in a unit volume with velocity between v and v plus dv. So if this is the number of stars in a unit volume within this range of velocities, then the amount of energy transferred by stars with impact parameter between b and b plus db within a time interval dt is going to be given by this quantity. So this is the sum of v squared, delta v squared perpendicular, is given by the distribution times the quantity that you want to find the sum. And this quantity here is the volume of the cylinder. 2 pi b, that's the circumference. db then gives you the area. And then the length here, which is v dt, gives you the volume. And then you integrate that in v. That will give you the amount of energy that is transferred by the stars that are within the cylinder. Let's consider then what kind of collisions we have before we do this integral. Consider first close encounters where the impact parameter is less than a b minimum. And as you imagine, in this case, because the collisions are so close, the velocity that is being added can be bigger than the initial velocity of the object. Oh, these types of collisions happen very, very rarely. We can see just how rare. What is the B minimum from the solar neighborhood? Let's estimate that. And we can see then what is the B minimum for the sun. So B minimum, again, is the semi-major axis of the hyperbola, which is given by this equation. If you plug in solar values, so m equal to 1 solar mass, put also the big M equal to 1 solar mass, the velocity being equal to 20 kilometers per second, that results in a B minimum of 10 to the minus 5 parsec, which is about 1 AU. So indeed, collisions this close are rare. None has happened for the sun in the age of the solar system, so they can be ignored. So the other type of encounters would be long distance encounters. So for long distance encounters, B is bigger than the B min. So each collision has only a very small impact, but there are many of these. So to find their cumulative result, let's integrate from B minimum to B maximum. For that, let's break this triple integral here, first in an integral in B, then in an integral in V, and an integral in time. So let's get the original equation and break it now into an inner integral here in B. After we solve that, we then integrate in V, and then finally we have it in T. This inner integral here then will become, so this inner integral here, let's call it I, and integrate it in here from B minimum to B max, and it would be the integral of delta V, B dB. Substituting out the value in the previous video that we found for delta V, then this is the expression that we have for I. You throw this integral here in sin pi or Wolfram alpha, and you find this result. Well, now let's substitute again the definition of B min, right, which is given in here. So using this definition for B min, we simplify the expression for I, the integral in B. Now let's introduce a variable here, which is B max over B min. Let's call this big lambda, capital lambda. And because we expected the maximum impact parameter to be much, much bigger than the minimum impact parameter, this 1 plus lambda is simply lambda. So this integral here becomes 4g squared little m squared over v squared times the logarithm of this lambda. Now we usually take b max to be the radius r of the system. Log lambda is called the Coulomb logarithm. The Coulomb logarithm measures the increase in cross-section that is afforded by the long-range force. If you did not have a long-range force, if you only had contact, your integral in impact parameter would be simply the geometrical cross-section of the system. It is this Coulomb logarithm that is quantifying the effect of the long-range force, which in this case is gravitational. Now, if you substitute B max by the radius and the expression again here for B min, then you find this expression for lambda. Some values of the Coulomb logarithm are 18 for the solar neighborhood, about 10 and 12 for globular clusters, and about 6 to 9 for galaxy clusters. But having found the integral in impact parameter B, we now need to integrate in velocity and time. The change in kinetic energy then, due to the sum of the individual encounters, is going to be given by this expression here. What we did here was to substitute I, the expression that we found for I, into this inner parenthesis here. So then we have this expression. Now, what we need here is to find what is the expression for the distribution. In order to estimate the cumulative effect of the collisions, then, what we are needing is to assume a form for the distribution of velocities. Now, observations in the solar neighborhood are consistent with the Maxwellian distribution of velocities. So what we have them is this expression. So integrating in V yields this expression, which you can write as, if we define it T, relaxation, as the inverse of this quantity. So this gives the relaxation time for a gravitational system. Now, for a system of n equal mass particles, with total mass m total equal to n times n, and where the particles collide with the typical velocity given by v squared equal to gm total over r, then the relaxation time would be, if we substitute the velocity dispersion by the typical velocity of the system, and we substitute the number density, little n here, by the total number over the volume. So big V is volume and little v is the velocity. Now multiply and divide both by the total number n. Substitute the volume by 4/3 of pi r cubed. And I'll substitute the velocity. G squared, little m squared, big N squared, and r squared gives you v to the 4th power. And now define the dynamical time as r over v. We have here then the relaxation time for a system of n equal mass objects. With these estimates then for the relaxation time and the dynamical time, we can apply them to some systems and verify the times. For an open cluster where you have n about 1,000 stars, the typical mass is about the solar mass, and the radius is typically 2 parsecs. The velocity dispersion 1 kilometer per second. You have that the dynamical time is of about 2 million years, and the relaxation time is about 50 million years. The age of the system is comparable. It's between 10 million years to about 1 billion years. So it's comparable to the relaxation time. So a very young open cluster is still undergoing relaxation. A globular cluster, say, the number of objects about 1 million, each star is about a solar mass, radius about 10 parsecs, velocity dispersion 10 kilometers per second. It has a dynamical time, get r here over v, about 1 million years, and the relaxation time is about 2 billion years. With a typical age of 13 billion years, globular clusters should be relaxed. For the solar neighborhood, you have the number density being about 0.1 star per cubic parsec, the mass, about solar mass, radius about 10 parsecs, VRMS is about, the velocity dispersion is about 20 kilometers per second, the dynamical time is about 200 million years, and the relaxation time is about 2 times 10 to the 13 years. With an age of about 10 billion years, the system is not relaxed. For the galactic group, for the local group, I have about 20 objects. The masses are 10 to the 11 to 10 to the 12 solar masses, the typical mass of the galaxies in the group. Radius of the group is about 1 megaparsec. The velocity dispersion is 150 kilometers per second. Plugging in these numbers, the dynamical time gives you 5 billion years. And the relaxation time is between 10 to the 9 and 10 to the 11 years. So with a system of an age of 10 gigayears, 10 gigayears would be 10 to the 10, the system is still undergoing relaxation. For galaxy clusters, you have about 1,000 galaxies, each one mass 10 to the 11 to 10 to the 12 solar mass. The radius is 2 megaparsecs. Velocity dispersion is about 1,000 kilometers per second. You find dynamical times of 2 billion years and relaxation times between 10 billion years and 10 to the 12 years. With an age of 10 billion years, these are still undergoing relaxation.